Line integrals part one. Calculus one, you integrate along a horizontal axis, possibly a vertical axis, and along the horizontal axis, a small change is dx, vertical is dy. Now we're going to integrate along the path. So there are certain summation processes that we can add up here that we couldn't do with a simple horizontal or vertical integration. We have this triangle, dx is a horizontal change, dy is a vertical change. Along this hypotenuse, ds squared is dx squared plus dy squared. You can derive these two formulas pretty easily, just doing some Pythagorean algebra. And if y equals f of x, then we'll use this ds formula, 1 plus dy dx squared dx with a square root. And if x and y are defined parametrically, then we would use this formula. It's just all a matter of what the problem starts with. We're going to go through two problems in this section, one where we use this, one where we use this. And then we'll have a follow-up video where we're talking about integrating a force through a vector field, which we can use to calculate work, which is pretty pertinent to physics. So, to begin, suppose we're going to add up 2xy ds, where s is this straight line path. X goes from 0 to 2. Just goes along this line segment from the origin to 2, 6. First of all, we're going to calculate ds. And ds in this case is square root 1 plus dy dx is just 3. And then we're going to multiply that by dx, and that's just square root of 10 dx. And that's actually a ratio between the horizontal change and the slant change, so to speak. If you were to take a small horizontal displacement of 1, for instance, the displacement along this hypotenuse would be 1 times square root of 10, 3.3 something. It's that simple. So ultimately, we're going to switch this to a dx integral. We're going to integrate along the x-axis, but we'll be adding up a summation along that path. So not that difficult. All we need to do is take this path integral and get everything in terms of one variable. And the variable, you could get x and y in terms of ds, I suppose, or you could get everything in terms of x or everything in terms of y, but it has to be in terms of one variable. So we will integrate, we'll do it in terms of x. You have to switch, if we're doing it in terms of y, you'd have to come up with a different ds formula. It would actually be 1 plus dx dy squared dy. You could certainly do that and differentiate this backwards. So we have 2x, now y can be rewritten as 3x. And then we want to multiply by dx, which is square root of 10, or ds. Then, of course, it's a dx integral, so x is going to go from 0 to 2. And then we have 6 square root of 10. That's a constant. X times x is x squared. We can integrate x cubed over 3 from 0 to 2. And plug in 2, we get 8 thirds. 6 times 8 thirds is 48 thirds, square root of 10. Of course, you can divide 3 into that. I could have divided 3 into 6, and we get 16 square root of 10. Whatever this represents. This could be density, by the way. This would be meters. If this were a density as a function of position, then kilograms per meter times meters would give us kilogram, and this would give us mass. So this could be a kilogram answer, for instance. There are other applications. We're not so worried about that. Now let's redo this. Let's suppose we had this problem expressed in a different format. Suppose x equals t, y equals 3t, and t goes from 0 to 2. You can see it's the same thing. X is t, put x in, y equals 3x. T is x, so x goes from 0 to 2. But just suppose that this problem is formulated this way. Well, we can calculate ds square root dx dt squared plus dy dt squared dt. And dx dt is just 1. dy dt is just 3 dt. If these paths are not linear, by the way, these integrals can get very, very difficult. As you could imagine, when you see square root of a squared plus u squared, what do you think of our old friend trig substitution? But we're not going to go there because it's too close to Christmas for all the weeping and gnashing of teeth that come along with trig substitution after all. So, well, guess what? This is square root of 10 dt. Now we have to redo our path integral to x becomes t, y becomes 3t, and then we have square root of 10 dt. Then we have to put in t limits. Pretty obvious we have the same thing. Sometimes these integrals look different, but they do always come out to be the same answer. If this was a different parameterization, I could parameterize this using some pretty interesting paths that would give us the same answer in the end. 6 radical 10 and then we have t squared, which integrates to t cubed over 3. We go from 0 to 2. Okay, and that's the same answer as we had before. We end up getting 16 radical 10, whatever it may be. Just one more note, if you're interested in an application of what this line integral could represent, especially this, you can draw a three-dimensional figure, x, y, z, and the path is this, where this would be the point 2, 6, 0. And think of this as a z function. Z equals 2xy. What does it look like along this path? Well, it's going to start out here. By the time that we get out here to 2, 6, 2 times 2 times 6 is 24. It's pretty high up. Well, this ends up being a kind of a curvy curve, so to speak. And if you take a small little rectangle, this dimension is 2xy. This dimension here is ds. So what's 2xy times ds? That ends up giving you area. And this could be an area integral, where we're adding up the area of some surface where the base ends up being defined by this path. That's one of the many applications of a line integral. So area before, we were confined to area of a plane figure, a two-dimensional figure. Okay, now we can have anything. This could be a curvy line, could be a zigzag line, could be a sine function, could be whatever we want, and we can find the surface area of this possibly contoured figure using a line integral. So we're expanding things. That's all for this video. We'll be back for part 2 shortly.